Nature's at COP26 to find answers to the climate science questions you've been asking. One question came from Dr. Meisner.
My question to you concerns risk. Why is risk as a topic not more explained? In the medical profession, this would be the point where we would initiate RCT studies for clinical data and try to get information on what effects and side effects our different interventions cause.
Dr. Meisner's insight into how the medical field would gather data about risk using RCTs or randomized controlled trials got us imagining the Earth as a sick patient. Now, one sick planet is of course very different to a population of sick patients, but it struck us that the climate scientists do something loosely similar to an RCT, just digitally. They build models. So we went searching for modelers in the hopes that they could give Dr. Meisner some insight into how a climate scientist calculates risk. And we found Richard Betts, who leads climate impact research at the UK's Met Office.
We can't do experiments on the real Earth, of course, because we only have one. We can't do a traditional control experiment, but we can use our models of climate and weather as a virtual laboratory, both to explain past changes in climate and make assessments of future changes.
Richard described how he builds his models.
So essentially the same mathematically based models that we use for the weather forecast in the Met Office. So a whole range of well-established equations for the laws of physics, the fluid dynamics, and also the representation of biological processes in the carbon cycle and so on. And approximations for some of the more kind of detailed processes to do with cloud formation and the changes of water from liquid water to water vapor and precipitation and so on, the energy balance of the Earth, basically the whole operation of the global climate system, including the atmosphere and the oceans and the biosphere and the global carbon cycle. So we can represent that within our models. We use the Fortran computer language, up to 2 million lines of Fortran computer code. Hundreds, maybe thousands of people have worked on the Met Office model over the years.
These huge models do their best to account for all the variables. But unlike in randomized controlled trials in medicine, climate scientists can't directly see the outcome of the interventions they're testing, only what their models predict might happen. But they have ways to try to make up for that limitation.
Now, in these models, you can't get a perfect representation. You don't know all the numbers perfectly accurately. So we have to have multiple versions of the models where we have a range of many of the key input parameters. And there's also other models as well produced by other centres. Using all these together, we can actually assess a range of outcomes, both of the past and future climate. So we can drive the climate model with past climate forcing, so how much CO2 has risen over the last 150 years or so, how the output of the sun has changed, how volcanoes have impacted the climate as they've erupted in recent years, decades and centuries, and then scenarios of future changes of the build-up in greenhouse gases to different levels with different assumptions about whether we cut emissions or continue to emit or even increase to our emissions.
And it's by comparing all of these models that scientists can start to make assessments of risk.
We can use this whole set of models to look at a range of responses, both in terms of the global climate and regional climates, changes in extreme weather, and look at the different ranges of possibilities. And it's very important not to look at the average of all the models. That can give you some idea of perhaps where you might be most confident. But in terms of risk assessment, you want to look at things that are possible, even if they're not the most likely. You want to look at the tails of the distribution. What is the 5% probability of an occurrence? And a lot of our work informs risk assessments, so that is really crucial to take that approach.